Before we look at a geometric view of the metric equation, let's look at a geometric view of the distance equation, Pythagorean theorem, which is telling us that delta d, that's the distance between point A and B, or between any 2 points, is delta x squared plus delta y squared. The distance squared, delta x squared plus delta y squared. And here, in this example, delta x, I should label my axes, delta x is 3, 1, 2, 3, and then delta y is 4, 1, 2, 3, 4. And so I guess I'll write this here. I could have delta x equals 3, delta y equals 4. And I could plug this into the formula. It's a 3, 4, 5 triangle. I would get 3 squared plus 4 squared. That's 9 plus 16, which is 25. And so delta d is 5. So I'll put this over here. Delta d is 5. That's the distance between these 2 points. And I guess I'm using arbitrary units here. You could think of these as meters, or if you like, inches, or whatever. All right, so how might this look in different coordinate systems? So here's another coordinate system, this clear sheet, that I can put on top. So these will be the red axes. And so, like this, these 2 coordinate systems agree. But I could come along and say, you know what? I don't like this business of B having a delta x. I'm going to come up with a coordinate system. I'm going to rotate my coordinate system so it's like this. This is my x, this is my y. Here's point B. And in this coordinate system, delta x is 0, and delta y is 5. So different delta x, different delta y, but we're going to get the same distance. So let me draw that out quickly. So in this red version of things, I could have a delta x of 0 and a delta y of 5. And if I plugged these into this formula, I would still get a distance of 5. 0 squared plus 5 squared is 0 plus 25. D squared is 25. D is 5, just like before. So we're going to agree, the plastic reference or plastic coordinate system and the paper coordinate system will agree. And of course, you might come along and say, you know what, I don't like either of these. I want to go like this. Let's see if I can do this. So if we go over here, twist them even more, now check it out. Delta x is now negative. Delta x is a negative 2, and delta y, let's see, it looks like it's a little, 1, 2, 3, 4, it's a little less than 5, right? So I'm going over this way. This is 5, that's a little less than 5. And it turns out in that system, in this coordinate system, which I'll do in blue, even though this is still a red axis, I could have a delta x would be minus 2, and then delta y turns out to be right around 4.6. And let's just see what happens if I try to calculate d that way. 2, or minus 2 squared, well that's 4, plus 4.6 squared, whole thing is, hey, right around 25. It's a little more because I rounded. 25.16. If I take the square root, 5.02. So all of these different coordinate values give the same value for the distance of d equals 5. All right, and so here's what I want to do next. Let's look at what this, try to think about this geometrically. So what this equation says, another way of viewing it, is that x squared plus y squared equals 5 squared. And that turns out to be the equation for a circle. And that's what I was trying to get at here. Like in this coordinate system, I move this around, and the thing that's always staying the same is that this point is always, point B is always 5 units from point A. So what that would look like, when I could plot these points, 0 and 5, 0 and 5, minus 2 and 4.6. I'm going to have to go off the graph here. If I went this way, 1, 2, and then 4.6. And if I graphed all the possible coordinate pairs that would correspond to this point B as I rotated this around, what I would get is a circle of radius 5. So I'm going to attempt to draw that. So we would get a circle. That's, for me, that's a pretty good circle that I drew. So the moral of the story here is that we can think of a circle as being the set of all points that is equidistant from this from the origin. And in particular, in this case, the radius of the circle happens to be 5. So now let's do something similar, but with the metric equation. So this is now a space-time diagram. I've got time and space x. And let's say I've got a point A that's at 0, 0, and point B that has an x of 3 and a t of 5. So what's the space-time interval from A to B? Well, we figure that out with the metric equation. So I can plug in delta t, that's just going to be 5, and delta x is 3. Again, I'm leaving off units just to keep things from getting too cluttered, but these could be meters or I guess seconds, because it's relativity. All right. So 25, this is 25 minus 9. 25 minus 9 is 16. So delta s squared is 16. So that means that delta s is 4. I'll put seconds on. So this space-time interval is 4 seconds. All right. I could, in another reference frame, suppose there's another reference frame, I guess I'll do this in red. Suppose there's a reference frame that has a delta x of 0. So this is the same, we're observing, imagine observing these same 2 points, but we're in a different reference frame where we observe that delta x is 0. What would delta t have to be? Well, delta t, I claim, would have to be 4. And to see this, delta s squared so there could be an observer in a different inertial reference frame who might have different measurements for these points A and B. And they could be x equals 0, t equals 4. And why do I know this is possible? Well, because this preserves the space-time interval. The space-time interval is the same. All observers in inertial reference frames will observe the same space-time interval between these 2 points. So I could draw this state of affairs, x equals 0, t equals 4, on this space-time diagram. and I would get that. Let's see. We could also imagine maybe there's some reference frame in which delta x is minus 5 seconds. And in that case, what would I get for delta t? Let's see, I guess I could take this equation and I could, let's solve it for delta t. So delta s squared plus delta x squared is delta t squared. This is just the metric equation rearranged. And then I know delta s has to be 4, because delta s is always 4. Observers will always agree on the spacetime interval. So I'm going to have 4 squared and minus 5 squared is going to equal delta t squared. Oops. 4 squared plus 5 minus squared equals, that would be 41. Take the square root. So there's some reference frame somewhere where the coordinates for B are minus 5 plus 6.4. Oh, and I didn't really prepare for this possibility on this, but I think we can recover. All right. I'm going to extend this way. Two, 4, 6. Okay. Okay. So this is minus 5. And then plus 6.4. Gosh, that's going to be way up here. So I could keep going like this, and the basically I'd be looking for pairs of x and t that satisfy this equation. So the equation is t squared minus x squared equals 4 squared. So if I connect the dots, right, and that's what I did here. We connected the dots, x squared plus y squared is 5 squared, and we got a circle. If you connect the dots here, it turns out that what you get is not a circle, but is a hyperbola. And these are curves that are shaped like this. So all of the points t and x that make this equation true are along this line, the original, the red, the blue, and many, many others. So this is a way to think geometrically about what the metric equation is telling us. So let me summarize and recapitulate a little bit what's been going on. So space and space-time, let's compare and contrast. So in space, we have points A and B, and x and y. This is space, not space-time. And there's some distance between them, and that's some real physical quantity that doesn't depend on your coordinate system. So everybody's going to see this same distance. If we rotate the coordinate system, we might get different values for x and y. What are all the different possible x-y pairs that would still be possible that would respect this physical distance? Well, that's described by this blue circle. So maybe over here, somebody would see a negative x and a positive y, and over here somebody might see a positive x and a negative y, but this formula tells me all the possible coordinate pairs that lead to this distance. All right, so now let's go over to space-time. A and B, these are points in space-time. So this is t now, time, and not position. So points A and B, they have some space-time interval between them, and that's given by this. And that's a frame-independent quantity. All observers in all inertial reference frames will agree on that. But their t's and x's might be different. What are all their possible t's and x's? Well, that's given mathematically by a hyperbola, that's this formula, and this blue line here. So there's a reference frame that would actually have a larger x and a larger t. And there's a reference frame where x is 0, and that's going to be the smallest possible t. And there's some other reference frame where x is negative and t is a little bit more positive. So not any pairs of t's and x are valid, only those that lie along this blue line. And so in relativity, we're interested in how time and space intervals look different to observers in different reference frames. And this geometric picture is going to be really helpful for us, particularly in Unit 6, when we're doing transformations from x and t in one frame to x and t in another. So our touchstone, both algebraically and geometrically, is that this is going to be the same for everybody. And that constrains or shapes how t and x are related from frame to frame. So I realize or suspect this is pretty abstract still. Maybe it's some fun or interesting little bits of geometry, but we'll see over the next couple units how this plays out and how this can be really helpful in thinking about relativity and coordinate transformations.